Hi, folks. This is Dr. Arbogast, coming to you with today's lecture on population viability analysis. Um, I often will refer to that as PVA for short. A reminder, you have two readings that go along with this lecture. You have one that's a short intro to PVA, which just sort of gives you an overview um, to what PVA is. And then there's one that's a case study on PVA on the eastern barred bandicoot from Australia. So those are both posted on Canvas for you. Okay, what is PVA? PVA is a process of one, identifying the threats faced by a species, two, evaluating the likelihood that the species will persist for a given time into the future, and three, its long-term objective is to promote conditions in which species retain their potential for evolutionary change without intensive management. PVA is used to address three aspects of threatened and endangered species management. One, planning, research, and data collection. In setting up your population viability analysis, you have to identify what parameters or factors are important and which ones tend to be unimportant. And that process in and of itself can be very useful. Number two, um, it allows you to assess the relative vulnerability of a population or species. And number three, importantly, it allows you to rank various management options. It allows you to pick the options that provide for the best predicted outcome. So you might remember this figure from earlier in this semester. Um, I used it to talk about trying to figure out the effects of inbreeding not a few lectures ago. But this is an example schematic of a population viability analysis model. And what it's showing is all the different factors that you could potentially include in a population viability analysis. Now, some of these you might have data for your species already. Others of these you might have to go out and collect data for. Um, and finally, we'll talk about doing a sensitivity analysis, which is a way to determine which of these factors or parameters are actually important to the model and which ones aren't. But basically, this is what sort of schematically a population viability analysis model might look like. Okay, so one of the main things that PVA is used for is to estimate the likelihood of a population going extinct. Um, it allows you to do this while you're comparing different proposed management options. You can see which ones lead to extinction rather quickly and which ones allow the species to persist for much longer. You can use PVA to assist existing recovery efforts, um, and it's frequently used in endangered species management to develop a plan of action. Okay, you develop a model, and that helps guide you to develop a plan of action, whether it's what new data you need to collect or what actions you actually need to step in and take. Importantly, it allows you to rank the pros and cons of different management scenarios. Okay, and we're going to see some case examples of that today. Um, PVA can also be used to identify key life stages or processes that should be the focus of recovery efforts. And in this example, we have at the top an adult frog and at the bottom the tadpole. And what that's just referring to is that we might find that increasing survivorship at the tadpole stage makes more or less of a difference than it does with increasing survivorship at the adult life stage. Okay, so a PVA is a good way um, to model at what life stage it's most important to try to increase survivorship or decrease um, the decrease loss of that life stage um, for a species. Okay, so what I want to do is walk through a couple schematics that sort of show you how population viability analyses work. Um, PVAs are the basis for what we call adaptive management of fish and wildlife populations. And by adaptive management, what we're referring to is sort of a, um, a repeated process where we collect data, build models, see how the models do, and improve the models, and repeat that. Okay, so I want to walk through a real simple example at the bottom of this slide, and then I'm going to go through a little more complex example just to point out a few of the high points. In essence, what we're doing when we set up a population viability analysis can be thought of as this schematic at the bottom. And I'm going to sort of start with the monitoring, which occurs out in nature, out in the field. Okay, so that's step one in this case. And the monitoring of a population allows for us to come up with estimates for the population size, for example, but also estimates for a bunch of the important parameters like age of first breeding or number of eggs laid, numbers of percent of juveniles that survive, and so on. So that on the ground monitoring work allows us to come up with estimates. The estimates then feed into our initial um, uh, understanding of what the population status is. Is it increasing, decreasing, stable, or whatever? So that's sort of part two. We use monitoring to assess, to come up with estimates of population status and characteristics of the population. Step three is to develop population viability analysis models. Okay, so these models, we're using that information in a lot of cases that we collected in the field. It might be incomplete, but we're using what we have. We're developing PVA models, and those models then are used to go back and predict the population status, and importantly, to predict what's going to happen to it in the future. We then see how well our PVA model works. And the way we see how well it works is to see what it predicts in terms of what's going to happen to the population. Then we go back to step one and monitor the population, and we update it with new information from the field. That then goes back to give you an updated population status, number two, and we just do this over and over until we improve our PVA model so that our model does a good job at tracking what is actually happening in nature. And so you repeat this many times. And as you do that, your models get better, you get more information and more parameters from your monitoring gets better, and pretty soon you have a good model that matches what is happening in the real world. Another way to look at it is this little more complex diagram, and you can sort of blow this up on your full-sized PowerPoint. But the first four steps are basically the ones that we just sort of talked about. Step one, you're sort of collecting data. Step two, you're determining your PVA model structure. Step three, you're estimating or refining the parameters, and the parameters are basically the values that go in the model. Step four, you're building or improving your model. And here's where I want to step in and say we can go two different directions. That's at step 5. At step 5, we can do one of two things. We assess the extinction risks and recovery chances. We can then either go directly to step 7, where we rank management options, selecting the best management plan for the survival of the population or species, or we can perform a sensitivity analysis, which is going from step 5 to step 6. Okay, a sensitivity analysis is one in which we determine which parameters make a big difference in the outcome of the model and which ones don't. So including them or not including them, does it make a big difference? If the value is small, does that make a big difference compared to whenever the value is large? Okay, so sometimes we do a sensitivity analysis with our model as well. In that case, we might go back then to step 3 and refine our parameters or our model based on having done a sensitivity analysis. And then we just go through again through step 4 and step 5 and then go down to step 7. Eventually you can see going from step 7, we go over to 8 where we implement the management plan, step 9 where we monitor the species long term, step 10 where we evaluate the data from monitoring, and then we go back and if we need to, we modify our model and we do it over and over again. So this is just like what I was showing you before. The biggest difference here is whether after step 5 we go ahead and rank our options, or we do a sensitivity analysis to figure out which parameters are having the most important effects in our model. Okay, so sensitivity analysis is determining which parameters make an important difference in our model. Whether we include them or not, does it make a difference? Does the value that we set for them make a difference? Okay, step 10, we can either modify our model and make it better, or we can go through and work on getting better estimates or refining the values that go into our model, the parameters. So a sensitivity analysis example, for loggerhead turtles, researchers found that survivorship through the egg stage ended up having not very much of an effect on population outcomes. In contrast, survivorship through the oceanic juvenile stage was found to be critical to population health. Okay, so when they did a sensitivity analysis, they realized that survivorship through the egg stage, whether you had that to be low or high, didn't make much of a difference. What did matter was survivorship through the oceanic juvenile stage. And so because of that sensitivity analysis, they were able to focus recovery efforts, which had been focused on egg survival on nesting beaches. Those could be redirected toward increasing juvenile survivorship of the oceanic stages, in this case by incorporating turtle excluder devices, or what we call TEDs, into fishing nets. So those are some of the cool things you can do within a sensitivity analysis. You can figure out exactly what parameters matter and which ones don't matter so much. One of the things that is really good about PVA models is that they tend to produce graphs that are pretty intuitive for people to understand. They do population growth graphs or time to population going to extinct graphs. They look a lot like stock market graphs, things that people that might not be biologists can view and intuitively understand pretty easily. PVA models can be employed to estimate the time to extinction or the probability of extinction within a given period, such as 100 years, for example. And this information and the models can be useful in convincing policymakers that a species could become extinct within a given time frame. And so over to the right, I just have an example of some of these charts. And uh, this is just to show you the kinds of simple graphs that PVA models can put out. And again, one of their real powerful things is that they produce these graphs that are relatively straightforward and easy for policymakers and other stakeholders to understand. They're not real complicated. PVAs are also useful because they force us to think about some things. For example, they force us to think about what are the demographic parameters for a particular population or species. Again, demographic parameters are population parameters, growth rate of the population, birth rate, and so on. They force you to ask, how should we analyze the data? How do we identify gaps in the knowledge? Okay. And when we do identify gaps, that helps us to determine what data should be collected in the future. PVAs also help us to understand the consequences of components of the models or parameters of the models. Okay, again, that's sort of the sensitivity analysis. It helps us to understand whether a certain parameter or component of the model has a big effect or a small effect in the overall outcome. And finally, to understand the consequences of changes in parameter values. Okay, so if we tweak a parameter just a little bit, does that have a big effect on the total outcome of the time to extinction, for example, or does it not? Building a PVA and conducting a PVA makes us think about all of these things, and the process of actually addressing all of these questions is helpful in and of itself. Okay, this last one, to understand the consequences of changes in parameter values, is an example, again, of a sensitivity analysis step in the PVA. Okay, so what, in essence, PVA is a method of risk assessment. It's a species-specific method, which means that you have to build your specific PVA model for each species or population that you're looking at. You can't just make a general one. It can be thought of as a marriage between ecology and statistics. It definitely has a statistical component, but it's founded in the ecological realities of the population or species of interest. And you can think of it as bringing together species characteristics and environmental variables to forecast population viability, and the risk that a population or a species will go extinct. So one of the uses of PVAs is to try and predict a minimum viable population size, or MVP, which can be defined as the minimum number of individuals required for long-term survival. We talked about this a little bit several lectures ago. But the idea behind the MVP is that if the population size falls below the minimum viable population size, it may then, fall into the extinction vortex, right? And so we would like to know what that minimum viable population size is, and we can get a handle on that through doing a population viability analysis. So in all cases, PVAs begin with a scientific question. The question that you're asking might be broad. It could be so broad to be something like, is this species at risk of becoming endangered or extinct? And if so, why is that the case? So you can start with a very broad scientific question when you start to do a PVA. Questions can also be much more specific. You could, for example, ask what amount of take or harvest is acceptable for bluefin tuna for the population to persist and thrive. Or you could ask a question, for example, is it better to release 30 California condors into Arizona or 15 condors each into Arizona and California? And you could model those and see which one produces the best outcome. Now, there's two different ways or two different types of models that we can use when we do PVAs. This is an important point that I want you to get, so we're going to spend a minute on it. The two types of models are deterministic models and stochastic models. And you might remember that we used the words deterministic and stochastic a few lectures ago when we were talking about the extinction vortex. In this context, they're a little bit different, but a deterministic model is one in which every set of variable states is uniquely determined. Okay, so what you're saying then is that every set of variable states, or every variable, or every parameter gets a unique value or a unique equation that allows you to determine that value. So a deterministic model is one in which every set of variable states is uniquely determined by parameters in the model and by sets of previous states in these variables. Therefore, deterministic models perform the same way for a given set of initial conditions. What deterministic models are basically classic mathematical formulas or algorithms. If you put the same starting value into a mathematical equation, you're always going to get the same answer out, right? It's like just like a simple equation. Okay, so you can think of deterministic models as classical mathematical formulas, or what we often call them are algorithms. In contrast, a stochastic model isn't a simple formula in the sense that the variable states are uniquely determined by parameters in the model and by sets of previous states of these variables. Instead, with a stochastic model, randomness is present, and variable states, or parameters, are not described by unique values, but rather by probability distributions. So a probability distribution, for example, that the value could be anywhere between 1 and 10, and the value that during a given run that is selected at random. Okay, so probability distributions define the parameters or the variables, not sort of simple, uniquely determined states that you would get if you used a classical formula or a deterministic model. Because of this, if we use a stochastic model, we can get a different answer each time we run it, even if we start with the same input at the beginning. And therefore, if we're going to do stochastic models, we need to run them a bunch of times and then look at the mean values and something about the variance in the outcomes, like the 95% confidence intervals. You don't need to do that for a deterministic model because you're going to get the same answer every time. Let's look at some case study examples where they use stochastic models just to help this drive this point home. Although PVAs can be somewhat controversial because they are models and so they have assumptions built into them, there have been a number of excellent studies that have demonstrated their utility. The first one that we're going to talk about is the spotted owl in old growth forest in the Pacific Northwest of the U.S. This was a really big a conservation issue in the 1980s, and a lot of work was done to determine basically how dependent the spotted owl was on old growth forest in the Pacific Northwest of the US. And in particular, in the examples I'm going to show you here, they looked at different configurations of old growth forest, different arrangements of how clumped it was versus how fragmented it was. So the first one that I'm going to show you is the result of a simulation model for the northern spotted owls under a configuration of old growth forest that was highly fragmented. And you can see that over to the right. This was a stochastic model, so it had randomness built in. And that's why when we look at the population size and the time on the x-axis, we see a dark black line in the middle that suggests that the population will crash to zero in about 100 years. We also see lighter black lines above and below the heavy black line. The heavy black line is the mean value, and the light black lines are the 95% confidence intervals. Okay, so the old growth forest being highly fragmented is indicated by the fact that each of the cells in the graphic to the right represent a patch of old growth forest, and you can see that they're pretty small and they are spread out from one another. So under that scenario, we would expect a mean population crash in about 100 years. Could be earlier than that. If we look at the lower 95% confidence interval, it would be about 60 years. Could be a little longer than that, but the mean time was about 100 years. So that's, again, the mean is the dark heavy black line, and the 95% confidence intervals are the lighter lines above and below it. Now that's changed the configuration of the old growth forest from being highly fragmented to being a single large block of old growth forest. So we've changed the configuration. Again, we're doing a stochastic model, but the outcome looks a good bit different than what we just saw, right? What we saw before was the population crashing at about 100 years on average. In this case, if we have a single large block of old growth forest, the PVA model, the stochastic model, suggests that after 100 years, the mean population size stays about the same as it does in the beginning. Now, we do have our 95% confidence intervals, and they're actually a little bit wider, meaning that the lower number and upper numbers are a little bit further away from the mean. But in general, this scenario looks like it's more promising, right, than the one we looked at before, where the mean of the population time to crashing would be about 100 years. In this case, after 100 years, the population is still going along at about the same population size as it was when it started. The third configuration they looked at was patches of old growth forest surrounded by buffer zones of younger forest. And this one had an interesting outcome. The mean actually went up a little bit in this case, and so we had a little bit of an increase of the population when we look at the mean, the heavy dark line in the middle. But notice how big the 95% confidence intervals are. And the lower 95% confidence interval actually decreases down close to zero after 100 years, while the upper 95% confidence interval tends to increase over that time. And so there's a lot more uncertainty with this configuration than there would have been with the single old growth patch. But these are the kind of things that we can do and they're pretty easy to understand and to convey to people. And again, these are just looking at different configurations of the old growth forest and using stochastic models, PVA models, to predict the outcome of the population size over a 100-year interval. Okay, the second case study example is on the eastern barred bandicoot from Australia, from an area called Hamilton. They used a stochastic PVA model also. You have a reading about this on Canvas, so you should look at it carefully. I'm going to point out just a few things, highlight a few things from this reading, especially on how they set up their PVA and some of their results here. One of the tables that you want to spend a good bit of time looking at is Table 1. These are the population parameters that they estimated, okay? And it just goes through and tells you what parameters they included in their PVA model. I'm going to blow up the top of it so you can read it a little bit better. They include things like first age of reproduction, litter size distribution, and mortality rates. Okay, these would have been values that they probably would have gotten from field observations, and they would have used them in their PVA model. If we go back, we can see that there are various things in there. One of the things they didn't include was genetic stochasticity. They didn't include anything about genetics in this study, but they did include a lot of other things. And this is just blowing up the bottom part of that table, showing that they included things like the frequency and severity of catastrophes, what the initial population size was, the annual population growth rate, and the generation time. And what they're showing here with this one, what they're showing here in Table 1 is what they call the basic model. So they started out with the basic model, and then they did some variations on this. And they looked at what happened to the population under the basic model and then under variations of the basic model. So at the top of Table 2, where it says scenario and it says number 1 basic, that means that it includes the parameters as listed in Table 1. If you look right below that, scenario number 2 is exactly like the basic model, except they took catastrophes out. Scenario 3, they doubled the catastrophes. And you can go down through the list, and they had 11 different scenarios that they looked at. And then they looked at the probability of extinction at 5 years, 10 years, 15 years, 20 years, and 25 years, and also calculated the mean number of years to extinction under all of these different scenarios. So if we look at the basic scenario number 1 and we go across, we can see that there is a 100% chance, 1.00 probability of the population going extinct at 25 years, and that the mean number of years to extinction under the basic model was 10.6 years. Under number 2, with no catastrophes, if we now take out catastrophes, so there's no fires or hurricanes or things like that, the mean number of years to extinction jumps a little bit to 11.9. Not a lot, but it does go up a little bit. If we double the catastrophes, as in scenario number 3, then we see that that's going to make the mean number of years to extinction go down some, so that they go extinct more quickly, so at 9.3 years. The best scenario cases have the population going extinct at around 19 to 20 years. And you can see that in that column to the far right, right? And so basically, the range goes anywhere from about 7.8 years under scenario 5 up to 20.6 years under scenario 11. So what figure 3 of the paper is showing is an example of some of the outputs from their stochastic models. Remember, you have to run stochastic models multiple times. This shows 10 different runs. Normally, you would run it hundreds or thousands or tens of thousands of times or more. We have the computing power to do that now. But in this case, it's showing the fates of 10 simulated populations of the eastern barred bandicoots with the population biology parameters as described in Table 1 under the basic scenario. So under the basic scenario, starting in about 1989, what we see is that most of the runs or simulations have the population crashing somewhere around 1996 to 1999, with a few outliers that allow the population to go out as long as 2007. Okay, but this is what the output from a stochastic model would look like, and we can convert that into a mean and a 95% confidence interval, so it looks just like what we saw with the spotted owls. Okay, if you were doing a deterministic model, you would only need to run it once because whatever you get as your output would just be repeated over and over as long as you put the same input in to start with. But with stochastic models, you have to run it multiple times and look at the means. You can also look at the frequency distribution of times to extinction. In this case, it's based on 10,000 computer simulations. And again, it's a stochastic model. And what you're looking for is the peak. And the peak suggests that the Hamilton population is going to go extinct in the late 1990s. Okay, again, this study started out in the late 1980s, started modeling it, and it was suggesting that although the population could persist into the 2010 or even later, if you see the right-hand tail, the peak of the graph is suggesting that it's most likely that they will go extinct in the late 1990s. So what I want you to do for next time is to actually Google the Hamilton population of the eastern barred bandicoot and look and see what happened to them. Did they recover? Did they go extinct? When did they go extinct? If they did, was it within when they expected, and so on. Okay, and to wrap up, there are some model packages to do these PVAs with. A range of approaches to PVA modeling, but there are commercial analysis packages available and they are free. One of them is called Vortex. It's been around for quite a while. Another one is called Ramus Ecolab. It's also been around for quite a while. I believe both of those are still available, but they allow you to build these PVA models and to run them. And so you don't have to, for example, come up with your own R package or something like that to do a population viability analysis. There are PVA packages, computer packages out there. So that wraps it up for population viability analysis, and we'll leave it there for today. Everybody stay safe and healthy, and you'll hear from me again soon.